Welcome back to Introductory Statistics, Math 15. We're looking at Chapter 1, Sections 4 and 5. In Section 4, the discussion was focused on critical thinking. And when you're doing statistical studies, and in particular when you get to your inferential statistics project at the end of this course, you're going to have to think about what information you're gathering, how you're presenting it, and whether it makes sense to people who would be observing this study. And one of the things you have to be careful of is garbage in, garbage out, or GIGO. It's very common in computer science to hear about garbage in, garbage out. If you put in data that's not valid, the analysis that you perform, no matter how meticulous you are with your statistics, will not be useful. So make sure that you spend the time getting data that's useful, that is unbiased, that is meaningful, then also perform the statistical analysis on that useful data. Graphical representations can be misleading. Sometimes people actually have graphical representations that, if it's an axis system, doesn't start at 0, and therefore when you look at that axis system, it could mislead you in terms of how large the interval is. If they jump from 500 to 550, and it looks like it's really gone from 0 to 550. Another graphical representation problem can be when you start having three-dimensional figures representing linear or one-dimensional data. The three-dimensional can magnify differences that really aren't there. When you collect data, it's very important that you get data that is from unbiased sources, and oftentimes if you just get data from voluntary sources, self-selected sources, then there would be a natural bias, and so you have to be careful about not collecting voluntary samples. Correlation and causation are two concepts that are often looked at as one implying the other, and that's not necessarily true. If you have two things that seem to be related, that doesn't necessarily mean that one causes the other. So correlation does not imply causation. And possible sources of misinformation, you can see the list here. We have reported results, meaning I tell you what my grade point average is, I tell you what my SAT scores were, rather than actually getting the data. You have to be careful about reported results. Make sure that you have samples that are large enough. We will talk about how to get sample sizes that are significant. For graphs, make sure that you represent accurately what's going on with the graph. Avoid skipping gaps or exaggerating differences. Pictographs, sometimes having 2- or 3-dimensional pictures exaggerates differences that shouldn't be represented in that way. Percentages sometimes are used to misrepresent, so you have to be careful on the use of percentages. Loaded questions. If I say in a survey, do you like Starbucks coffee? Or if I say, do you love that new mocha coffee from Starbucks? You can influence the response based on how you ask the question, so make sure that you don't load your questions with bias. The order of questions can also influence responses, so really think through how you order questions in surveys. Non-responses should be analyzed because sometimes those non-responses give you information, so don't just dismiss non-response. Missing data is often a problem with surveys or with studies, so make sure you account for missing data. If it's a self-interest study, you are doing a study for your job, and you know that the results could influence your job or influence your company, that could introduce bias into your study. Precision of numbers. Sometimes if you list out extra decimal places for numbers, it seems to indicate that those are really significant, and actually the information may not be to that level of accuracy. So only use the precision necessary for the particular problem, and then try to avoid deliberate distortions. Do not mislead people in your gathering or reporting of data. In Section 5, we're looking at specific categories of data collection. And so if we have an observational study, influence the subjects, do not modify what you're observing if possible. Whereas in an experiment, you are specifically going to treat the data or treat the things you're going to observe in some way. And then after you apply the treatment, you'll observe the effects of the treatment. That's specifically for experimentation. So that's the difference between observation and experimentation. If you're trying to gather a simple random sample, that's a sample of n subjects that are selected in a way that makes every possible sample of size n equally likely. So you're looking for collections or groups, and you have to guarantee that each group that you select was equally likely to be chosen from all the other possible groups of size n. Whereas a random sample is simply a sample where each individual member in the population was equally likely to be chosen. So simple random sample, choosing groups of size n, every individual member should be equally likely to be chosen. And then a probability sample is a sample in which each individual member of a population has a known chance of being chosen. So for example, throwing a die, you normally, when you're throwing a six-sided die, have every value in the die equally likely, 1 out of 6. But if you have a loaded die, maybe 1 or 2 of the numbers are going to occur more often than the others. And so as long as you know the probability that each of those is going to occur, we could call that a probability sample, gathering the information from that die. A systematic sample is a sample selected by choosing a starting point. So I have this collection of data. I'm going to choose some place to start, and then from there I'm going to choose every kth element. So maybe I'll choose every 10th or every 25th, and that's how we will systematically select my subjects. Convenient sample is something you should always avoid. If I'm at Moore Park and I go out into the quad and I say, I'm going to just look at the people who walk by me and ask them a specific question. Well, that's convenient for you, but it's not necessarily gathering a good representative sample. So try to avoid convenience and really look at techniques that will give you randomness and representation. Stratified sample, sometimes you want representation from multiple groups. So in a stratified sample, you can actually break the population into subgroups. For example, a high school has students broken into freshman, sophomore, junior, and senior, and then guarantee that you select subjects from each of those subgroups. That would be a stratified sample. Clustering would be that you break the population into, or the sample into, subgroups, and then you select randomly a subgroup and then use everyone in that subgroup. So this would be at Moore Park College. We've broken students into classes, and then we'll just randomly select classes, but then use every student from that class. That's a cluster sample. Cross-sectional study is a study in which you observe over a specific period of time. Or actually, not over a long period of time, but over at a particular period of time. You study and observe and measure and collect information just at that one point in time. Whereas in a retrospective, you're going to actually go back and look at previous time periods and gather data over those time periods. Longitudinal is futuristic in scope. You're looking forward and you're going to gather information over a period of time in the future from groups, often called cohorts, that share common factors. You're going to be looking for these types of techniques when you're actually creating your particular project for your inferential statistics study. Randomization is the assignment of subjects to different experimental groups using random selection. So I can assign you to a group, but I'm going to randomly select you before I put you into the group, rather than with some bias try to put you into groups. Replication, the repetition of an experiment. If you're doing experiments, it is often necessary, especially in scientific institutions, to verify that you can replicate your experiment. If it can't be replicated, it makes it less likely that people would respect the results. Blinding is a technique of hiding information related to the treatment. So if you are actually going to perform an experiment and you do have some treatment, making sure that the participant in the experiment does not know that that treatment has occurred is called blinding. Confounding is the inability to distinguish among effects of various factors. So if you are unable to determine whether these factors in the experiment did affect the outcome, you call that confounding. And then finally, controlling effects of the variables, planning experiments that minimize the possibility of confounding. There's one other term that I want to mention here in terms of blinding, and that's called a double-blind experiment. A double-blind experiment would mean the person participating in the experiment and the person conducting the experiment both would be not knowledgeable of the treatment. For example, a famous placebo effect is something that occurs when someone is given a treatment, a medication, and they know they're given the treatment and therefore they feel better. Well, if neither the person administering the treatment and the person taking the treatment know whether it's a placebo or the actual medication, that's called a double-blind experiment.